But anyways, moving on. We get a new mission. Cool little mission here. This is to Psyche. Psyche is the name of the mission. So they are once again going to an asteroid. This is NASA, who I'm speaking about. They are going to a metal-rich asteroid to try and find what really makes up these planets that are in our solar system, and what can this tell us about planet formation? So, Psyche is both the name of an asteroid orbiting the sun between Mars and Jupiter and the name of a NASA space mission to visit that asteroid, led by Arizona State University. The mission was chosen by NASA on January 4th, 2017 as one of two missions for the agency's Discovery program, a series of relatively low-cost missions to solar system targets. So, the Psyche spacecraft is targeted to travel to the asteroid using solar electric low-thrust propulsion, which I will talk about. Following a Mars flyby and gravity assist. After arrival, the mission plan calls for mapping the asteroid and studying its properties. So you can see, boom, off Earth. It's already launched. So it's currently going right there. And then it'll circle around and then come back towards Mars. Mars will give it a little bit of a gravity boost. And then it'll come all the way out here. Boom. Get to Psyche, approach it, then kind of slow down, start orbiting it, and then end the mission. All right, so once the spacecraft arrives at the asteroids, plans call for it to perform science operations from 4 staging orbits, which become successively closer. So this same thing happened with the asteroid Bennu mission, or Bennu mission. They first got to the asteroid, and then they made, I think it was also 4 basic orbits around the asteroid to kind of map the actual surface of this. All right, so now let's get into the spacecraft. This physical, that's the spacecraft right there. That's currently what's out in space. The Psyche spacecraft and solar panels, which will be built by Maxar Technologies, are about the size of a singles tennis court. The body of the spacecraft is slightly bigger than a small van and about as tall as a regulation basketball hoop. The spacecraft will include a gamma ray and neutron spectrometer, a multispectral imager, a magnetometer, and X-band radio telecommunications system. The Psyche mission will also test a sophisticated new laser communications technology called deep space optical communication that encodes data in photons to communicate between a probe in deep space and Earth. So there it is compared to a tennis court. This is a big spacecraft. And then this is the actual place where they'll have the majority of the instruments on, whereas this is including the solar panels. All right, we'll talk about this propulsion system. So the spacecraft will be propelled by solar electric propulsion. Very, very cool here. I have some cool things about this particular type of propulsion that they will be using. But yeah, so they'll also have this, I guess, these antennas, magnetometers, just kind of trying to get what the makeup of it actually is. So here's where the spacecraft is currently, right? This is exactly where it is. So let's try and zoom way out. There's the Earth back here. Here is Psyche. And then you'll see we can fast forward a little bit. You'll see it getting further and further away. I don't know. Come all the way out here. Kind of loop-de-loop. And you'll see it coming in right here for that Mars gravity assist. Get that Mars gravity assist. Boom. Meet up with Psyche. Boom. right there. Very, very cool. All right. All right. So, like I said, the propulsion system, we will talk about in that in 1 second. Let's talk about the launch. Another cool thing about this was it was launched on not a NASA rocket, but a private corporation rocket, SpaceX. The Psyche mission launch occurs in Phase D. NASA selected SpaceX of Hawthorne, California to provide launch services for the Psyche mission. Psyche successfully launched at 10:19 Friday, October 13th, 2023, aboard a SpaceX Falcon Heavy rocket from Launch Pad 39A at NASA's Kennedy Space Center. View the overall launch schedule and coverage information. Look at that. There it is, taken off right there. Once the Psyche spacecraft is fully assembled with the solar panels, which fold during transport and launch, the spacecraft is shipped to Kennedy Space Center, Florida. At the launch site, the team conducts an entire recheck of the spacecraft before integrating with the launch vehicle. There you see it blasting off right there. All right. And the spacecraft will travel 2.2 billion miles on its mission. So very long journey for it. Once in space, the spacecraft travels using solar electric propulsion. Solar electric propulsion uses electricity from solar arrays to create electromagnetic fields to accelerate and expel charged atoms, ions of xenon to create a very low thrust with a very high efficient use of propellant. Here it is right here. This will be the first use of Hall effect thrusters beyond lunar orbit. So, okay. Why didn't I mention the propulsion? Because it's the first time that they'll be using it. And I had no idea what a Hall effect thruster was. They looked cool, but what is it? You see this picture right here. You're like, whoa. Now, on the podcast before, long time ago, I played Kerbal Space Program on the show, and maybe I should do it again. Maybe do a mock mission to like Mars or something. But yeah, so I did that on the show in the past, and in that game, they do have a electrical propulsion thruster, just like they do right here, and it's kind of the same thing where it uses xenon gas as its fuel source, and it has very low thrust, so it's not very powerful, but it can last for a very long time compared to a chemical rocket that we think of when we think of rocket engines. So, all right. All right. NASA is preparing to travel to a world unlike any other it has visited before. Following its approval of a Discovery mission in February this year, a spacecraft set for launch will visit the main belt asteroid Psyche, a metal world that scientists think is made up entirely of nickel and iron. The nickel-iron makeup of Psyche suggests that it may be the exposed core of an early protoplanet, torn apart by hit-and-run collisions during the early history of the universe. All right, so it will be orbiting all of this stuff. Those requirements led the mission team of JPL scientists and engineers, as well as researchers at Arizona State University, to turn to the NASA Glenn Research Center, leaders in solar electric propulsion for decades. Remember, it's got to travel 2.2 billion miles, so it's got to have a good engine on it. NASA Glenn in Cleveland, Ohio, has been developing and testing solar electric propulsion technology since 1964. Solar electric propulsion uses electricity generated from solar arrays to ionize atoms of the propellant xenon. These ions are then expelled by a strong electric field out of the back of the spacecraft, producing thrust. So, in short, SEP is a propulsion system that is a combination or coupling of solar array technology and ion thruster technology. Charge up your thing using the sun, and then use that thing to get the xenon gas and or particularly the ions of the xenon gas. So you're not actually shooting xenon gas out. You're shooting these tiny particles out the back. And that's what's helping you move a little bit further. The SEP thruster planned to be used by Psyche is the SPT-140 Hall effect thruster, produced by SSL, the subcontractor with JPL for the mission. To achieve the science objectives once in orbit around the asteroid, the SEP thruster must perform in a new way that required a new round of testing that could only be conducted at NASA Glenn. They tested that thruster before, but they had not throttled that thruster to lower levels. They had used it at a higher level, but they wanted to know how we can expect it to behave at a lower throttling. So that is what we're testing. We were able to simulate it to give them enough data to understand that. The SPT-140 Hall effect thruster was put into the large thermal vacuum chamber at NASA's Glenn Electric Propulsion Laboratory. It is the largest and best equipped facility of its kind in the world. They started September 5th and completed testing September 18th. All right, here we go. That thruster is normally rated at 4.5 kilowatts operating power. For Psyche, the trajectory is such that they would like to throttle down or go to a lower gear for large parts of their trajectory. There are a bunch of reasons they want to do that. They want to have some power. They don't need as much thrust. They want to operate in a little different mode than when they are actually at the asteroid. Because it's a 4.5 kilowatt thruster, most of the previous testing was done at that throttle point. For Psyche, they want to go all the way down to 900 watts. So part of this test was figuring out how much we run this thruster down and there at that throttle condition. How do we run this bigger thruster with less power stably? The testing was critical to understand how the thing would form. They used vacuum chambers as well, and I'll show a video of them putting this into the vacuum chamber as well. What we've observed, unfortunately, is that Hall thrusters are sensitive in terms of how they perform to that ambient pressure condition. Other places don't have a pressure chamber like this. Okay. All right. The testing yielded crucial data for mission planners about how the thruster will perform during the important on-orbit phase of the mission. The dethrottle is a function of the science that we want to do around the asteroid. It gives them more time for their science instruments and imagers to do what they need to do. The instruments planned for the Psyche spacecraft include those different measuring devices that we talked about earlier. I think it's exciting to go out and go look at that kind of an asteroid. I think it may give us clues about the beginning of our solar system. Anything that can give us those kinds of answers is wonderful. At first glance, the test results confirm our predictions regarding how the thrusters will perform. It looks like everything is working as expected, but we will continue to refine our models. And then here's a video of them putting this actually into this giant vacuum right here. You see, you can kind of see the scale of how big this is as well. If you look at some of these ladders right there, I'd imagine those ladders are probably 6 feet tall, maybe 10 feet tall, but this is a pretty humongous facility or vacuum right there. And that's the thruster right in the middle right there. There's a person right next to it for scale, but this is them putting it into this giant vacuum. Very, very cool. Now, so let's watch a video on how thrusters work. This is from Umish PEPL. This was a fantastic video. Please go support him, because this was an amazing video. Because I mean, what even is ions? What is this? How does this thing even work? Because this is what's ultimately going to be used for the first time this far away from our planet. So let's hope that this thing works.
Hall thrusters are a widely used type of spacecraft propulsion device. Instead of combusting a chemical fuel like a typical rocket, Hall thrusters employ electricity to ionize a propellant, which can then be accelerated by an electric field to produce thrust. This produces much less thrust than a chemical rocket, but is far more efficient, enabling missions which carry more payload for a fixed launch mass, and which in some cases can even be faster than those launched by a chemical rocket. Let's take a look at how one of these devices works. Hall thrusters have only a few key parts. There's a discharge channel, typically made of a ceramic, a metallic anode, and a hollow cathode. To start the thruster, we apply a voltage between the anode and the cathode. This sets up an electric field, which causes electrons emitted from the cathode to migrate toward the anode, completing the circuit. Electromagnets embedded in the thruster produce a magnetic field perpendicular to the electric field. Since electrons orbit magnetic field lines, this field acts to halt the electrons on their path from cathode to anode. The combination of crossed electric and magnetic fields also induces the electrons to rapidly circuit the thruster at speeds approaching and even exceeding 1,000,000 miles per hour. This so-called Hall current gives the thruster its name. At the same time, a neutral gas, typically xenon or krypton, is injected at the anode and begins to diffuse downstream. Ever so often, a drifting electron impacts a neutral atom. Sometimes these collisions have enough energy to knock an electron off of the neutral atom. This produces a positively charged ion and a second electron, which joins the Hall current. The more electrons there are, the greater the probability of collisions, and in this way, more and more ions are produced in a process known as avalanche ionization. The resulting fluid of ions and electrons is known as a plasma. The positively charged ions in the plasma feel the applied electric field and are accelerated downstream at tens of thousands of miles per hour, producing a small amount of thrust. Enough electrons follow them such that the device remains electrically neutral overall. Every time an electron collides with a neutral or an ion, it loses a small amount of momentum and drifts a bit closer to the anode. In this way, the electrons are able to complete their path from cathode to anode despite the presence of the magnetic field. However, the electron current that actually reaches the anode is much higher than what we would predict even when accounting for all types of collisions. The cause of this enhanced, so-called anomalous transport is unknown and is an active area of research. However, as a result, we cannot simulate these devices in a way that predicts their thrust, efficiency, and other key performance metrics from their geometry and operating conditions alone.
Very,
My research at the University of
very.
Michigan's Plasma Dynamics and Electric Propulsion Laboratory focused on improving our model.
Very cool. So that's how they work. You can also, to the right here, see a little simulation, but I'll turn off the volume. That's kind of how they work. They shoot this stuff from the anode, this xenon gas, into these charged particles. And as a result, they hope that they hit a xenon molecule to one of these ions, and then a reaction occurs where they'll be able to release energy. So, it basically doesn't sound extremely like 100% foolproof, where you can get a constant stream of thrust, it seems like. Now maybe that's different for the Psyche mission. Now this is a year ago when this video was actually created, but maybe they've improved since then. And like we talked about, they need to kind of control what the actual thrust is. They can't have it at a constant 4.5 kilowatts. They need to bring it down to about 900 watts. Now I can't really translate how much the actual thrust that is, so I just know it's a decrease overall. But with these engines working how they do, it's not super reliable. But so far the tests for Psyche are good, and obviously the spacecraft launch, so they must have figured it out for the most part. So this is what's going to be propelling the basically tennis court sized spacecraft through space. They'll be using this technology, firing the xenon gas, hitting these charged particles, and then they collide, they bump into each other, and then they release a positive charge, or they release, there's a reaction I know I literally just watched the video and I still can't explain it, but they come in contact, they butt heads, then they release a small amount of energy out the back, and then that energy being released out the back is what propels it forward. So that's how these things work. And that's basically the Psyche mission. It's not I would not say that it's a mission that is as important as the Bennu mission for me in particular, because the main thing for me has always been life on this planet, life on other planets. How did we get here? Why are we here? Um, that's kind of where I am drawn towards, but that's certainly to some people not the most important thing. This mission is going to be about the cores of planets and how planets themselves formed in our solar system and how they do in general terms, so that we can discover new worlds and get a better understanding of how they formed themselves. So it's a cool mission. But speaking of Bennu, let's talk about it, because while I was gone, they did release some info about it. They opened up the capsule, and I think that they'll find some real discoveries. They did a press conference. I suggest you go to NASA's YouTube page and watch. They did about 2 hours on the mission and the mission and opening up the particular capsule, and they had a bunch of people from NASA like head up in NASA. Like they had the director, Bill Nelson, I think his name is. He was there, and they did a presentation on basically some of the stuff that they found. But let's get into some of the stuff that they found. So this is from NASA. This will be a first little article, kind of doing a little overview of the whole thing, and then we'll kind of dive deeper in. NASA's Bennu asteroid sample contains carbon and water. In this picture right here, that is actually the sample right there. So when I originally had talked about the mission, I wasn't able to get video, but I explained it, and I'll re-explain here how they got the sample. So they have a canister at the bottom that comes out of the spacecraft, and they have obviously areas inside of that canister to collect samples. But to get the samples into it, what they do is they bring that canister down to the surface, and from inside they fire nitrogen gas, basically not straight down, not 90 degrees out of the side, but on an angle into the ground. And as a result, the ground or the soil breaks apart, and it kind of goes up into the air, and some of that trajectory is ultimately going to go into the canister, and that's how they get the sample. So right here is where you see said sample. So very cool. Initial studies of the 4.5 billion year old asteroid Bennu sample collected in space and brought to Earth by NASA show evidence of high carbon content in water, which together could indicate the building blocks of life on Earth may be found in the rock. NASA made the news Wednesday from its Johnson Space Center in Houston and showed off the material for the first time. This finding was part of a preliminary assessment of NASA Osiris-Rex mission. The Osiris-Rex sample is the biggest carbon-rich asteroid sample ever delivered to Earth and will help scientists investigate the origins of life on our own planet for generations to come. Almost everything we do at NASA seeks to answer questions about who we are and where we are from. NASA missions like Osiris-Rex will improve our understanding of asteroids that could threaten Earth while giving us a glimpse into what lies beyond. The sample has made it back to Earth, but there's still so much science to come, science like we've never seen before. I talked about this in the main Bennu episode. They are sending that spacecraft now. They have this sample here back on Earth, but the spacecraft that it came from is still going to another asteroid that they expect to either come close to or ultimately collide with Earth in a couple of decades to see if maybe they could either stop it or maybe they could investigate what's going on with this particular asteroid. So the OSIRIS-REx mission is still not over. Although more work is needed to understand the nature of the carbon compounds found, the initial discovery bodes well for future analysis of the asteroid sample. The secrets held within the rocks and dust from the asteroids will be studied for decades to come. All right, and then they kind of go into a little bit more right here. The goal of the OSIRIS-REx sample collection was 60 grams of asteroid material. They spent 10 days so far carefully disassembling the sample return hardware to obtain a glimpse at the bulk sample within. When the science canister lid was first opened, scientists discovered bonus asteroid material covering the outside of the collector head, canister lid, and base. There was so much extra material, it slowed down the process of collecting and containing the primary sample. Within the first 2 weeks, scientists performed a quick look analysis of the initial material, collecting images from a scanning electron microscope. That's a big boy microscope. You see very small things, infrared measurements, X-ray diffraction, and chemical element analysis. X-ray computed tomography was also used to produce a 3D computer model of one of the particles, highlighting its diverse interior. This early glimpse provided the evidence of abundant carbon and water in the sample. As we peer into the ancient secrets preserved within the dust and rocks of asteroid Bennu, we are unlocking a time capsule that offers us profound insights into the origins of our solar system, said Dante Loretta, OSIRIS-REx principal investigator. The bounty of carbon-rich material and abundant presence of water-bearing clay minerals are just the tip of the cosmic iceberg. These discoveries, made possible through years of dedicated collaboration and cutting-edge science, propel us on a journey to understand why not only our celestial neighborhood, but also the potential for life's beginnings. For the next 2 years, the mission's space team will continue characterizing the samples and conduct the analysis needed. NASA will preserve at least 70% of the sample at the Johnson Space Center. All right, and more than 200 scientists around the world will explore the regolith properties, including people from the U.S. and Japan and Canadian Space Agency, other scientists around the world included. Right, and then, yeah, that's kind of it. Let's get into a little bit more of the actual discovery. This is posted 8 days ago. The initial glimpse are very, very, very promising. All right. Let's see. Let's scroll down. Yeah. They think it's about 250 grams of actual material, but they just opened it up. Let's continue. The bounty of carbon-rich material and abundance presence of water are just the tip of the cosmic iceberg. The discovery made possible through the years of collaboration and cutting-edge science propel us on a journey to understand not only our celestial neighborhood, but also the potential for life's beginning. With each revelation from Bennu, we draw closer to unraveling the system of our cosmic heritage. The journey isn't over for OSIRIS-REx spacecraft, by the way. It's going to this asteroid Apophis. It's going to hit in 2029. All right. Asteroid won't collide with Earth in the next century, but its scientific impact will be tremendous. It won't hit us for at least 100 years. So that's good to know. It's estimated to be about 1,100 feet across and could cause serious damage to the planet's surface if it were to hit. The asteroid poses no threat for at least the next century. What happens after that? Because I don't expect to live until I'm 100, 25? I guess I'm 25. Until I'm 125, right? However, if I have kids, say when I'm 30, by the time that they have kids, grow old, retire, and are maybe in their 80s, then maybe this could potentially hit them. And I certainly don't want my kids to be negatively affected by a major asteroid that crashes into the planet. Apophis is in the category of potentially hazardous asteroids. Asteroids with orbits that bring them closer to Earth now and for centuries in the future. What makes Apophis the poster child for potentially hazardous asteroids is that it will make the closest known approach to Earth of any large-scale asteroid this decade. However, let's not panic. The three most important things about Apophis are it will miss the Earth, will miss the Earth, will miss the Earth. Although Apophis will not hit Earth anytime soon, the asteroid will make a close encounter with our planet on April 13th, 2029. Will pass just 19,000 miles. That's closer than most geosynchronous satellites and 10 times closer than the moon. Because the space rock is so enormous, Apophis's close passage will be so bright that over 2 billion people in the Eastern Hemisphere will be able to witness it with the naked eye. Yeah, you can see where it's going to be. You see right where those... Oh, man, there's a lot of stuff up there. Classified as an S-type asteroid, Apophis also contains a mix of metals, including nickel and iron, which is the primary reason why they also want to visit this place, much like the Psyche mission. They kind of want to understand, was this an early center of a planet? But they're also trying to do other science, whereas the Psyche mission, that is just strictly to look at, was this an early planet, and how does this inform us on how planets formed? The excitement of Apophis discovery turned to concern when researchers calculated just how close the asteroid's orbit would bring the space rock to Earth. From the visual observations taken in 2004, researchers calculated there was approximately a 2.7 chance that the object would hit Earth in 2029. 2.7. Okay. By 2006, the probability was all but negated by additional calculations. But future impacts, particularly of the asteroid's flyby in 2068, could not be dismissed as easily. The path of Apophis after 2029 will depend on how Earth's gravity changes the asteroid's orbit. Okay. If Apophis' path through specific gravitational keyholes, the gravity of the Earth would tweak its orbit by just the right amount, or should I say the wrong amount, to put it on a collision course in a later year. Because astronomers were unable to track Apophis from 2015 to 2019, it was too close to the sun, so you literally could not see it. Further progress ruling out a 2068 impact was not forthcoming. So it might hit. Nice. The asteroid seemed almost stubbornly determined to live up to its apocalyptic name. When the asteroid once again moved away from our star and thus could be better observed, they resolved to tackle the problem in 2068. At JPL's Center of Near-Earth Satellite Studies, we compute high-precision trajectories and assess the possibility of future impacts for all known asteroids. That's our daily bread and butter. Unseating Apophis from the top of several space agencies' risk list was no easy feat. Fornokia and his colleagues wove together radar and optical tracking data in late 2020 and early 21 to come up with a precise trajectory for Apophis, according to a statement from NASA. The team then combined this newly acquired data with years of intense observations to come up with a clearer picture of Apophis's trajectory. Apophis has been extensively tracked since its discovery by both optical and radar telescopes. Thanks to these data, we can precisely predict the motion for Apophis through the April 2029 flyby. The team calculated that the orbital period of Apophis, or time it takes to orbit the sun, will be stretched from 0.9 years to 1.2 years as a result of the asteroid's encounter with Earth. Perhaps more significantly, data from 2020 and 2021 observations allowed the CNEOS crew to model how close Apophis will come to gravitational keyholes that correspond to potential impacts with Earth in both 2036 and 2068. The CNEOS team also ruled out a potential impact for the next 100 years. Okay. Okay. All right. Yeah. So maybe it might be over 100 years. So we don't have to worry about it this century, which is good. I won't have to worry about it, but maybe my grandkids will, which is scary to think about. One, that I'm going to have grandkids, hopefully. But two, that they might also be wiped out by a. Well, I don't know if this is going to wipe it out. Let's continue reading before I make that claim. Predicting the effect of an Apophis-like asteroid hitting Earth is not easy. There isn't anything like it in the geological record of our planet. Other impactors have been either much larger, such as the one that killed the dinosaurs and caused the Cheeks Club crater, or much smaller. And factors such as asteroid size, density, and mass, as well as the angle and velocity at which the asteroid strikes, all affect how much damage a hit can cause. Keep that in mind. There are many factors to what creates big explosions. We have run simulations of an impact between Apophis and Earth, but at 340 meters across, the outcome of an Apophis scale impact with Earth is very uncertain. Size and speed are the main factors, but the nature of the target site is also important. If the impact occurs in the ocean, it can generate hazardous tsunamis on land. A lot more ejected dust is produced. All, of course, is a major factor is how close the impact happens to human populations. Collins estimate that if Apophis were to strike Earth at 45,000 miles per hour, the average speed of asteroid impacts, the energy released would be about 10 billion joules. This is equivalent to the explosive yield of the global nuclear arsenal, about 100,000 times more than the energy of the Chelyabinsk meteor and 1,000,000 times more energy than the bombs dropped on Hiroshima. Huh? Let's continue reading. The worst case scenario for an impact this size would be if it were to occur close to a large population center or near a heavily populated coastline, Collins said. If this were to happen, devastating consequences would arise from a number of secondary effects, such as violent ground shaking, intense thermal radiation, and atmospheric shock waves. Unless an asteroid similar to Apophis hits Earth and we can measure the consequences, our program may remain a best guess. All right. Interesting. All right. Let's see. Earth Impacts Effect Program. Let's look at this. Welcome to the Earth Impact Effects Program, an easy-to-use interactive website for estimating the regional environmental consequences of an impact on Earth. This program will estimate the ejected distribution, ground shaking, atmospheric blast wave, thermal effects of an impact, as well as the size of the crater produced. All right, distance from impact. Let's do everything in feet and miles because we're Americans. Let's say this happens in, like, say, New York or something. So we'll say 500 miles away. Impact examples. Okay. Chicks Club. This is what wiped out the dinosaurs right here. Dang. 17.5 kilometers across. All right, this is one that landed in Russia. Okay. Meteor crater. All right. Let's do 50 meters. 50 meters, since that's what? Not 550. Density? Let's do one that's kind of in the middle. I guess dense rock. Impact velocity. All right, I guess we'll do this in kilometers. I guess we'll do 17, right on the dot. Typical velocities are 70 kilometers a second for asteroids and 51 kilometers a second for comets. Impact angle. Yeah, we'll do 45 degrees, so it kind of hits us at an angle. Water of depth. We'll start up water of depth. Dude, near the coastline, so let's say about 500 feet. Calculate effects. All right. Okay, I'm about 800 kilometers away. That is 500 miles. All right, and it's about 164 feet in diameter. Traveling about 10.6 miles per second. Yeah, it's going to be hitting 500 feet of water over crystalline rock. All right, energy before atmospheric energy, 6.78 megatons of TNT. The average interval between impacts of this size anywhere on Earth is 871.7 years. So every technically 871 years, you're going to get at least one asteroid that contains basically almost 7 megatons of TNT. And I think Hiroshima was 10, maybe 15. So this is pretty strong. The Earth is not strongly disturbed and loses negligible mass. The impact does not make a noticeable change to the Earth's tilt, less than 5/100th of a degree. The impact does not shift the Earth, so it doesn't really affect the Earth. Begins to break up at an altitude of about 54,000 meters or 177,000 feet. Bursts into a cloud of fragments at an altitude of 7,470 meters or 24,500 feet. Residual velocity of the projectile fragments after burst is about 5.82 kilometers a second or 3.61 miles a second. The energy of the air burst is about 6 megatons. No crater is formed, although large fragments may strike the surface. The air blast, this is basically the air that gets pushed out by this thing and basically just explodes. Air blast will arrive approximately 40 minutes after impact. Peak overpressure. I guess this is just pressure that's increased. Max wind velocity, 0.561 meters per second or 1.25 miles per hour. Sound intensity, 48 decibels. Now, keep in mind, I am 500 miles away from this happening, okay? So 48 decibels, and we'll get an air blast in 40.7 minutes, traveling from 500 miles away, and we'll still feel 1.25 miles of wind velocity. Impact generating tsunami waves arrives 6 hours after input. Tsunami wave is less than 10 centimeters at your location. All right, so here in Pittsburgh, I won't have to worry about that. All right, let's do another one. Let's do one, and then we'll move on. But Let's once again do 500 miles away, but we'll make this meters. We'll make this. What should I do? Here's what I'll do. I'll rank it up. Instead of 50 meters, let's do 50 kilometers. Projectile density, we'll still keep it a dense rock. I don't need it to be iron. Let's try it out. 8,000 kilograms per meter squared. Impact velocity. Let's have this one come in a little bit faster. Let's say it comes in at 30,000 kilometers per second. So it's cruising in. Still, let's actually drop this down to 40-degree angle of where it comes in. Water of depth. Let's say it goes into like middle of the ocean. So let's say we got about 5,000. So it's not hitting land, but after we'll see what happens if it hits land. Let's calculate these effects. All right. 31 miles across, as dense as possibly can be, coming down at 18.6 miles a second. It's going to be 0.9 miles over crystalline rock. Oh, good Lord. All right. Energy before atmospheric entry is going to be 5.63 times 10 to the 10th power megatons TNT. So very hard to even imagine. This is billions, trillions of times the Hiroshima bombs. Billions and billions of times stronger than all of the nuclear devices dropped at once. So this is gonna do some damage. All right, the Earth is not strongly really. The Earth is not strongly disturbed by the impact and loses negligible mass. The impact does not make a noticeable change in the Earth in the tilt of the Earth's axis. Depending on the direction and location of the impact, the collision may cause a change in the length of the day up to 940 milliseconds. Does not shift the Earth's orbit noticeably. Okay. All right, crater dimensions. The crater opened in the water has a diameter of 382 miles. So even the crater created by this thing, I'm 500 miles away. This is over half of the distance just to me. So pretty big. Crater formed on the seafloor because we're, 5,000 feet above water. There is a diameter of 233 miles wide and 82.3 miles deep crater formed on the floor of the sea. And the final crater is 506 miles in diameter and 1.38 miles deep. Volume of the target melted or vaporized is 318,000 cubed miles, so not square miles. Roughly half the melt remains in the crater, where average thickness is about 7.47 miles. All right, time for maximum radiation. So this is the heat felt off the impact right here. We're 500 miles away. All right, maximum radiation 41.2 seconds after impact. The fireball appears 334 times larger than the sun. Duration of irradiation 4.46 hours, and radiance relative to the sun is 10,200 times more radiant than the sun. Affects clothing at night. Much of the body suffers third-degree burns. Newspaper ignites. Plywood flames. Deciduous trees ignite. Grass ignite. So, one, you're going to be burnt. You're going to be burnt pretty bad. Major seismic shaking will approximately be 2.68 minutes after impact. The Richter scale magnitude is 11.8, greater than any earthquake in recorded history. Damage negligible in buildings of good design and construction. Okay. But eject. So I would imagine that there's pieces that break off of it. That'll arrive in about 7.27 minutes. Each one will be about 1,100 feet in thickness and about an inch in diameter. So these are pretty crazy. Air blast coming 40.7 minutes after the fact. I mean, compare this 3,380 psi to the other one, which was a percentage of a percent, very small number. Max wind velocity here is 8,770 miles per hour, and it is 148 decibels, dangerously loud. And this is all 500 miles away. Multi-story wall-bearing buildings will collapse. Wood frame buildings will almost completely collapse. Multi-story steel frame office buildings will suffer extreme frame distortion, incipient collapse. Highway truss bridge will collapse. Highway girder bridges will collapse. Glass windows will shatter. Cars and trucks will be largely displaced and distorted. Up to 90% of trees blown down. All right, tsunami time. The tsunami wave arrives approximately 1.8 hours after impact. It is between 1,910 feet and 0.7 miles, or 582 meters and 1.2 kilometers in height. So this is dangerous. However, there's no major global changes. So you know what that means. Let's have some global changes. Let's crank this up. Why only do kilometers? Why only do 50? What if we multiply this by 100 and we make it 500? Let's go for it. Let's go for 1,000 kilometer wide with the max amount of density. It's iron. It's 1,000 kilometers wide. It's hitting the Earth at. Let's go for it. Let's go for it. It hits the Earth at 72 kilometers a second. But we're going to be a little bit further away. We're going to be 1,000 miles away from this. All right, so we should be safe, right? This is hitting in 5,000 feet of water. Actually, I should do 10,000. Middle of the ocean. Deepest point of Earth. It's not hitting land. Let's test it out. Come on. All right, so the last one was 10 to the 10 megatons of TNT. This is 10 to the 15. Yikes. All right. So there is definitely some. What? Okay, we got to go bigger. We got to go harder for the next one. Something that is 1,000 miles across. Or no, we're 1,000 miles away, and the thing is 621 miles across. Okay. And it's hitting us at 44.7 miles per second. It's screaming it. All right. So it releases a lot of energy, but 5.64% of the Earth is melted. Does not make a noticeable change in the tilt of the Earth's axis. And the Earth is not strongly disturbed by the impact and loses negligible mass. So next time we'll go even higher. See what happens. Depending on the direction and location of the impact, the collision may cause a change in the length of the day by up to 5.1 hours. All right. The crater opened in the water has a diameter of 5,810 miles. Yeah, life would be over, unfortunately. All right. The diameter in the sea floor is 3,500 miles wide, 1,200 miles deep. The final crater is 11,000 miles in depth, 3.49 miles. This is the volume of the target melted is, I mean, you see right here. It is the entire Earth. Wow. All right, ejecta. This should be a little bit bigger if it'll let us. It won't let us do it. All right, that's fine. Let's go back and make this 5,000. Let's do 10. Let's multiply this by 10 because I want this to have some effect on the Earth. Keep everything the same. We'll drop this down to 70,000 kilometers a second. And we'll do this. Okay, everything's the same. All right, the last one was 15. This is now 18. 10 to the 18 power megatons of TNT. The Earth is completely, here we go. The Earth is completely disrupted by the impact, and its debris forms a new asteroid belt orbiting the sun between Venus and Mars. Yeah, we're gone. Very, very cool. Very cool. Very cool. We got way off track there. Way off track. I got Carmela waking up. She's trying to get me to throw the ball around with her. I did get off track, but that was interesting to see. So, asteroids potentially hurting us, potentially coming to destroy us. The Bennu mission, very cool stuff. And overall, the Osiris Rex mission as well.